Good morning. Today is the last session on climate and comfort. Then next week we have the presentations. This is the schedule. So this is the last one on climatic issues. And then we have the case presentations next week. And after that we started a new part of the course, the solar analysis, which is given by a colleague, Frank de Trooijer. At the end of the session today, I will also explain what is expected by next week. But so what we will do today is look at monthly. Instead of looking at monthly values, we look at hourly values. So that's the big difference with last week. But otherwise, there is not really something new. So the comfort analysis remains the same, just the data based on which we will do the analysis is different. So today we will mainly focus therefore on what are hourly values, what do they mean, what's the meaning of them, what's the difference with monthly values, and where can you find these data. Again, there are Excel files provided on Toledo in the module of today, where you will have to input your own data in order to have the graphical representations, which are prepared for you, but just the data needs to be replaced. And then I will show an example case to show you what you can do with the data and what is expected for the paper then. So first of all, why hourly data of what is it exactly is? What's the purpose? Well, it gives you very much more detailed picture of a certain situation where you are designing in. So it gives a better representation of the climatic context. It therefore also allows to more accurately analyze the thermal comfort, because if you just have monthly values, it means you have maybe a minimum and a maximum and an average, but you don't know every day how the climate or the weather is changing day by day and even hour by hour. Hourly data are sometimes also necessary if you want to, for example, make dynamic energy simulations to estimate the energy performance, so the energy used in a building. You need these hourly values. So based on monthly values, we cannot calculate in a dynamic way. So see how the building reacts dynamically on changing values. So an example of such a program is Energy Plus. It's a free software developed by ASHRAE, so the American Society for Heating and Air Conditioning. And what it does, well, you give in input. You need to describe your building in the program. And you need to describe the environment, so the climatic context or the weather data. And based on that, the program calculates the indoor temperature, for example, in your building. And then if you change a parameter, for example, you change the insulation value of the walls, or you change the window ratio, so the amount of windows you have, you can see how that changes the indoor temperature. If you also give information on the persons and the activities they do in the building, the program can also assess the thermal comfort in the building. But then you need to know who is in there, which kind of clothes they are wearing, what kind of activities they do, because that influences the comfort. And the output of the comfort is assessed in this software by the PMV, so the predicted mean vote that we have seen last week. So it's just a number. And there's another model as well used there. Then if you set your comfort requirements, if you say, I want to have an indoor temperature of that so many degrees during daytime and during nighttime it's different, or you set the humidity expectations, then the program can also calculate how much energy you need to obtain this or to guarantee this temperature inside. So it calculates, once you have the system, either it's net energy, and then you not need to model the heating system or cooling system. It's a net energy demand. If you do include also the modeling of the heating and cooling system, you can also let the program calculate the energy load at the end. So that's what this kind of programs do. But to allow that to have this assessment, you need this hourly data. And that's the input on this side here. So that's the environment, it's the hourly data. So it means a source for the hourly data is moreover this website of the program where they provide this data for many locations. Now, if we talk about hourly data, what does it mean? So for your location, you can find hour by hour a temperature and relative humidity and a wind speed and so on. What are these values? What do they represent? Well, they're fictive years. So there's not measured, it's not a measurement of a certain moment in a certain year and then have it consistently over the years. What it does, it composes, so it's a composition of different months which are well representing your climate data. So each number you see is a real measurement, but it's not necessarily for each hour the measurement of the same year. So what they did is they analyzed typically the data, the weather data of 30 years. So it's a long period. They have data of 30 years. Can be measured data or can be data from a climate model. Both are possible. But they have hourly values for 30 years. And what did I want to do? Extract, based on statistical analysis, of these 30 years, the best representing values. So for each month, the month best represents the 30 years. So it's not an average value. So one doesn't. So if you have 30 values, for example, for the first hour of January, because you have 30 years, one does not calculate the average of these 30 years. What one does is for each month, select the most representative one. And how is that done? I will explain in the next few slides. But so it's about representing these 30 years in the best way possible, but not averaging values. That's the big difference with the monthly averages we saw in the previous lesson. So it's based on a statistical analysis. How it's done, I will explain in a few more seconds. And of course, we have seen that climate is typically represented by different variables, weather parameters. So you had temperature, you had radiation, you had rainfall, you had wind speed. So it means that we need to choose also which of these parameters we will select for selecting the most representative year. Because you could do it on temperature, but you could also use radiation or precipitation to select your most representative month. So the methodology behind sometimes differs. So if you find fictive years hourly values, there are different ways of selecting these. So it's not always the same method behind. And that's why you see typically different kinds of results. So you have the test reference years, which uses different variables, for example, than the international weather year. So it's a different method behind, or a typical meteorological year, the TMY, is again based on different parameters or variables. But I come back to that in the next slide. So in summary, we have data, hourly data for 30 years based on observations or based on models, climate models. And from these 30 years data, we extract one representative year, which is not an average of the 30 years. How do we do that? Well, there are different ways. So it's based on statistical analysis, and typically it's based on selecting for each month the month that is most representative. So it means that you combine, for example, so imagine you have data from 1990 till 2020. What you do is you select the January month out of these data, which is most representative for these 30 years, and you do the same for February, March, April, and May. So it means for January, in such representative year, it's the values of 1 year, one specific. So you don't vary within the month. It's a month that is well representing the 30 years. But so it means you could, in a fictive year, you might have a combination of January of 1990 and February from 2020 and March from 1995 and so on. So each month is selected and should be best representing the full 30 years. But in that sense, it's fictive, because it doesn't exist, it hasn't happened, or it's not coming up from the models. It's really a combination of different months. But at the end, it should well represent these 30 years. It also means if you have data from 1990 till 2020, your representation is for that period. If it's data from 1920 to 1950, the representation is for then. And we know that climate is changing, so we should keep that in mind. And if we have information on which period it is representing, we should be critical on what we are analyzing. Now, as said, there are different data sets representing these 30 years yearly weather data. So the first one, which is very often used, is a test reference year. So it's the TRY files. which also have this extension at the end, so you can recognize it based on this extension. And what they do, they based on the statistical analysis of 30 years, they look at the temperature, the radiation, and the humidity first. It gets an equal weight, so they're evenly important to select the most representative one. And they then do a statistical analysis, and based on these 3 parameters, they select the most representative ones. So you have January from 1990, for example, but it could be that in that year, the wind speed or the wind direction is not well representing the full 30 years, because they make their selection based on temperature, humidity, and radiation with an equal weight. In the second step, they also look at wind speed, but only once they have selected a first selection, they then check if it's well representing, yes or no, but it's in a second step. So they only make changes if there's really high deviation. And then the TMY, for example, that's a typical meteorological year. So you will see the extension TMY, makes a combination of many more variables, so many more weather parameters, but with a different weighting. So the most important there to define the representative year is the temperature, so the outdoor temperature, the mean temperature. But they also look at maximum temperature and minimum temperature, but to a lesser extent, to have a good representation of the extremes, so in the morning and the afternoons, let's say. They also look at the dew point temperature, so to see how humid the climate is, minimum, so morning, afternoon, morning, and on average. And then the wind speed is also included. Besides the temperature, the second very important one is the radiation. So the radiation and the temperature are the 2 mean variables, but the others are taken into account as well, but with a lower importance, let's say. Then the IWEC, International Weather Year for Energy Calculations, these are the ones we're going to use typically. Sometimes you will find a test reference year, but most of the time we will use this one. It's again a combination of different parameters, looking mainly at temperature and radiation, but there are also the others, very similar to that one, but with slight difference in the importance of the indicators. And then you have even more, but so it means it's always the same. One have data of 30 years. A statistical analysis is made of some parameters, so either an equal weight temperature, radiation, humidity, or a more complex weighting of variables, and then the most representative months are selected, and a fictive year is combining these several months from different years. And that you will notice, so when you download the files for your situation, you will see that the dates are published. So you will see that January might be from a different year than February, which is again from, so 1980 might be combined with 1999 and so on. So that's why you will see these different dates, but each month will have the same date. So it's typically per month that has been composed. Where do we find the data? So typically the main source is where we have these energy simulations, dynamic energy simulations, because these programs require it as an input. So there they provide typically the data, and that's where we're going to look also for our files. So the most important one, so if you have your computer in front of you, you can have a look immediately. So energyplus.net, and then the weather tab, where you will see that they have weather data for the whole globe, let's say, so the different continents. And then you can either use that to find the best location for your situation, or you can also search by giving in a name of, for example, a certain country to see if there's any data set available. You can also look graphically on the same, so there's a browser as well to look in the map, because that's sometimes easier to find a good location if there is no location of your specific spot. Because we've said before, it's not always good to take the data from a weather station that is closest by, because there could be a mountain in between, or it's much higher or whatever. So with using the map, it's sometimes better to find a location that is well representing your specific situation, rather than just looking at a town that you know that is close by. So check always if it's well representing, and if you don't find a better one, at least mention in your report why you think there could be deviations from the real situation. And then for each location, so you can zoom in. If you found a location, for example, for Brussels. So in Belgium, we have 3 locations where there are hourly weather data. So at the coast, the north of Belgium, in the middle, and then in the south of Belgium, the Ardennes. So they have 3 locations, which are quite different, actually. So that's why there are 3 spots. Once you have then selected the location, you can download the files, and we typically download the folder, but I'll come back to that in a second, where you then can further analyze the data. But so you can also go just by a list and look and select first the continent and then go deeper and deeper. So that's another way. Okay, once you found the data, what kind of data do you find inside? And then I will go on how we will analyze it, or explain how we will analyze it. So again, this is the first graph I presented in the previous session, showing that there is a different information if you look at hourly value and monthly value. So what you did last week, or what you have been looking for this week, is searching for the data, one value as a mean value for each month. So one mean temperature for January, for February, for March, and then a minimum and a maximum. That's typically have 3 data for temperature, which gives you an idea on how the temperature typically, what's the average, but also what's the morning temperature and evening temperature typically of that month. But you see that you lose some information in the sense that you don't grasp how it day by day changes, or hour by hour the temperature can change. So giving this detailed blue line, that's what we're now going to analyze, you see that it's sometimes you could have the same mean, minimum and maximum temperature, but still have a big difference in how it actually is over the day. Or day by day changes. If you need heating, yes or no. If you need solar protection because one day is really hot and the other not, that you cannot really grasp based on average data because you calculate a mean. So that's what we're going to do now. We will first look for the hourly data, not only for temperature, but also for radiation, for wind speed, for wind direction, precipitation, humidity, and then we will compare. Again, we will assess the thermal comfort, and then we will compare if we make different considerations if we have this hourly data than if you would only have considered the monthly data to see how this gives more information or not. So how are we going to do that? First of all, we need the data. So you're first going to look for a good location to represent your site. And then you're going to download the data, and then we're going to process them again in graphical way in the spreadsheet, which is online, which I will explain now. To download the data, there are some steps to be taken to transfer the data in Excel, because it's structured in a way that the Energy Plus software can easily work with it. But now we need to transform it in an Excel that we can read the data to make the graph. So there are some steps to be taken in Excel to well represent it before you can have the graphs available. So that's why the next slides are a bit more technical, just explaining for those who don't have good experience in Excel how you can transform the data to a readable format. So first of all, you download them. So you go to the website and you download the data. It's typically a file that you will download with the extension EPW. So that's the extension of the file. You have it on your computer, and then we will change it to a comma-separated file and then an Excel file. But let's go step by step. So first of all, when you find the data, so for example, I'm now at the same website, but I'm looking at Brussels. And then you can see that you can download different files, the one that you need. So we won't download the textile, for example, but we will download the file with the EPW extension. Once you have saved it, you change the extension from EPW, just delete it, and you replace it by CSV, which means comma-separated values. Because if you just look at the EPW file, you just have numbers, all numbers, but it's really hard to know what belongs to what. So what we first of all do is separate each value by a comma. That's the only thing what you do by changing the extension and read out the file. Then you will get one long column only one column, and in each cell in the column there will be all values belonging to each other but separated by a comma. That's the first step. So a comma-separated file is just how the data are structured. This is the outcome. So once you so if you want to try, you can do it. So you have the file, you open it in Excel, and then this is the outcome. So if you click on the first column on whatever cell, you will find this content of that cell. So for example, it's 1986, so it's the year 1986, the first day, the first year, and it's the 20th hour, for example. So each line is 1 hour, the data of 1 hour. But all information is in one cell. So if you click on a cell on the second column, it will be empty. There's nothing there, because all the information is stored in the first column, but separated by commas. What we now want to do is separate it. We want to have only one value, one data set per cell. So we're going to change the data, which is now stored in one column, to spread it over different columns. So each comma should change to the next column, so that we have all the data in columns. So what we want is actually transfer it to this kind of file. So it's the same data, but instead of storing everything in the first cell and separated by commas, every value is now put in the next column. That's what we are aiming for here before we can make graphs out of it. Is that clear what we are doing here? It's a bit technical, but that's a step we need to take to make our graphs. Now, what do you see in these columns? So what kind of data do you have? So typically on top you see your location, so you can check if it's indeed the correct file, that you didn't make a mistake. So it's in Brussels. It's Brussels, the country of Belgium, here you see. And then you can find all the hourly data below. So the first rows on top are other information, but the columns below, once you see this same structure coming again and again and again, these are the hourly values that we're going to use. And then on top, you, for example, also see the warmest year, and the warmest week, sorry, and the coldest week in this climate. It's not always, it depends a bit on the climate, but here you see that for this typical year, the warmest year is typically from the 6th of July to the 12th of July, and then you also have the coldest periods. This can be interesting for a specific thermal comfort analysis, to look at the extremes, for example. Because in the graphs, we will make it on a yearly base, but you can also choose a period that you want to assess in more detail. And this could be a helpful direction to which values you should have a deeper look at. And then the colder year. Now, what is in the columns? Because there is no title above, so it's not so user-friendly, but what's in the columns? The first column is the year, and you see here that in January, it's represented by the January month of 1986 in my case. In your country, it will be a different year, because it's not always the same year. And if you scroll down, and as soon as you get to the second month, so if you come here to S2, that's the February, it might be a different year. That's this concept of representative year, where each month might be selected from a different year. It can be by coincidence the same year, but that's a coincidence, so it's not on purpose. The third column is the day, so here I'm still at the first day of the first month. If I take away this, you will see you have 24 hours in the first day, and then you come to the second day, and you will have again 24 hours, and that's how it's structured. Now, for each hour, you have a lot of data here. What do you see here? The first thing you see, so the 60 is the number of minutes. So it's 60 minutes in that hour that have been considered. Then you have a text column with some data sources or uncertainty flags, which is, for example, that there were no measured data and we took an estimation, for example, but we will not go in detail on that in this course. And then you have the real values that are of interest for you. So from after the text column here start the real data that you're going to use. So the next one here is the temperature. So it's a dry bulb temperature. Then you have the dew point temperature. So it means at what moment you typically have the change from a gas to water. So so it's a temperature where the humidity is too high, and so we get water in the air, so it's changing. And then we have some more, the relative humidity. It's an important one, as we saw for the climatic context. So this one and this one are the most important for the thermal comfort analysis. And then you have the atmospheric pressure, and then you have the radiation. And typically it's the total horizontal radiation, the direct radiation, and the difference between the two will be the indirect radiation, but I'll come back to that. So we have most of the data readily available, but the program in Excel will also calculate some differences to represent some other variables more explicitly. Oh, sorry. Now, how do we make this? How do we come first from a column with all the data to this data spread over the different columns? So what you do, once you have your comma-separated file, you open it, and you select the first column. And you do that by clicking on the A on top. If you click on this A, you will select the full column. And then you go to, on top, to Data, the Data tab. And in the Data tab, you find the text to columns function. So it means it's really going to change text and spread it over columns. That's the function of that button. If you click on that, you get this window. And here you now need to specify how the data have been separated. We have separated them by commas. So for each comma, the program should spread the data, take a next column. So here you should indicate comma. Sometimes it's by default set at a tab or semicolon or space, and change it to comma. And then you click on Next, and then you will get to a new window where I think maybe I should just do it. Yeah, let me first explain, and then I can show you by doing. You get to a next window, and then you can click on Advanced in that window. If you click on Advanced, it's important because we have decimal separator as well. So imagine you have a temperature of 7.2 degrees. Some programs use the point as a decimal separator, and some use the comma as decimal separator. So we need to make sure that this is indicated in a good way here. Otherwise, your comma will be used again as a separator, column separator, and that we don't want, so we need to correct it here. So what you do once you click on Advanced, you get this new tab, and then you need to ensure that the decimal separator is a point and not a comma, because otherwise you have an issue with our comma separated values. So it's a dot. So, and the 1000 separator is a comma, but typically it's not used, so it's nothing. So please put here a dot on top for a decimal separator to be sure that the values are read in a good way. And then you can save your file once you have done that, but then save it as an XLSX, so an Excel file, not as a comma separated file anymore. So it's an XLS file. Once you've done that, we're going to paste these values in the Excel file that is already on Toledo, and then the graphs are automatically made. Is that clear for everybody until now? You can try it out later on and tell me if it wouldn't work. You could even try it out with whatever climate file. It's just that you check that you understand everything. So once we have the data now in separate columns, we're going to paste them in the Excel file that is provided. In the Excel file that is provided, it's called Test Reference Year Analysis. And here I put it for Brussels, but we'll need to replace the data by your data, of course. The Excel file consists of different tabs, which you will find at the bottom of the file. The first one is explaining what you need to do, what's in the file. So the first thing what you need to do, if you don't have macros enabled by default, you need to enable the macros, otherwise it won't work. If you don't know how to do that, let me know. And then you paste the data that you have just made, the whole sheet, not just the first column, but the whole sheet. We will paste it here, and then we will see that in the next steps all the data are provided. So what kind of output does the Excel file provide? First of all, we have this yearly temperature, which is a completely different picture in Brussels than you saw before where it was for Cuba. Then you have the humidity, the same figure. So we have hourly data, the program automatically calculates the mean values, which you can then compare with the first values you already derived in the previous session. You have the hourly radiation values, and then you see different lines here. So the top one is an average of the hourly values you see here. And this is the sum of two types of radiation. On the one hand, you have, I think, the below one is the red one is a direct radiation, and the blue one is the indirect radiation. And the sum of both is the total radiation. What's the difference between the two? A direct radiation is when you have no clouds, and the sun directly hits you. The radiation of the sun directly hits you. When there are clouds, you still get radiation when the sun is there, but then it's dispersed, so you get a diffuse radiation. So the more diffuse radiation you have, you know there are more clouds, and that should also be reflected typically in the humidity, for example. So these are linked. So by analyzing these all, you can well understand how the climatic context is. So if you have a lot of direct radiation, more than the indirect, you know you have a lot of blue sky days when there is no clouds at all. And here you see the same again, but then this is on a monthly or a daily and a monthly basis, and here it's hour by hour to show that there is a variation. Then the wind is calculated as well. There are different graphs in the Excel file. So first of all, before you get these graphs, I go back, you will need to press a button in the Excel file itself, but I will show you in a second. You need to press a button to calculate, because if you don't press the button, the values that are shown there are still the old values from Brussels, though. So it's not refreshed. Even if you have deleted the values, the graphs are still the ones from the previous version. So the graphs are not remade as long as you don't press that button. So that's one to run the macro, and only then these graphs are redrawn. So it's important, otherwise these graphs, even if you have deleted the data and replaced it by your own, will still be the graphs from Brussels, which is the basic data I've put in the file. So you have to run it, the macro, and then you will get we call this a windrows for your specific context. So what it shows, this is the north on top. And these are the different, so this is the south, different directions, and you see where the wind is coming from. So the direction of the wind is where it's coming from. So it's typically here in Belgium coming from the southwest. We typically have a southwestern wind. You can also you see here a graph with an average over the day. So we see typically that we have more wind. The wind speed is higher during noontime than during the other hours. But that, of course, can differ month by month. So we see, for example, that we have lower wind speeds in April and higher wind speeds in January. So we can also see how it changes over the year. And that can be important. Why? If we have a climate where it's very hot and dry, and we want to use the wind to ensure that we can have a comfortable indoor climate, we should orient our building to the right direction. So we should know the wind direction. And we should also check if the wind is coming from the same side in winter, maybe then when it's colder, we don't want the wind. So it helps you in using the wind to cool down in summer, but maybe you should block it in winter time. So that helps you to see the variation. The file also gives you this windrows for each month. So then you can see if there's a big variation, then you should take this into account. And here you can also see the distribution of the wind speed. So typically the wind speed is around 3 meters per second. That's the most frequent speed here in this location. And it typically has this kind of variation. So the high wind speeds are rare, while the most frequent ones are here between the 2 and the 4, let's say, meters per second. For your context, it could be more to the beginning or more to the end, but the extremes are typically not so frequent. So this is on monthly basis. You see that the wind in Belgium is not changing too much, so it's typically coming always from the same direction. but in your context, it could be very different. All right, and then in the second step, we will use the same data for the comfort analysis. But maybe let me show you first the Excel file and how it works before we go to the thermal comfort. So let me just open the file from Toledo. That's maybe the best. So if you go to Toledo and you go to the course documents, do you see my screen? Yeah. You will go to the third module. So first of all, this is a file to show you again what kind of data is in each column. So we've put it there because once you have downloaded, you cannot see what something is. And that can be helpful. Why? It's the data automatically graphically presented. So on the one hand, you don't need to look at the data, but sometimes the graphs are not showing anything. Then it could be that there is just no data available, but then you can check here if the data indeed are in the file, yes or no. So some locations don't have wind speed, for example, or don't have radiation. Then you can check, or maybe you just copy-pasted something wrong. That could be another reason. So, but then you at least can check if the data is there, yes or no. So that's why we've put this file also there. And then let me look at the other one. Yeah. So in the first step on the bottom here, you see just the explanation that I've shown before. So what steps you need to take and then how you can present what's on which chart. So from Olga onward, it's about thermal comfort. So now what I have explained until now are the first two tabs. So let me show you, and then the wind as well. So first the data. So I first need to enable content here. So you see here automatically in most tool or Excel versions, the macros are disabled. To make sure that everything is running, you first need to enable it. Once it's enabled, the calculations for the wind especially will be possible. So here what I did, I first downloaded my data. I transferred from column to data over the columns, and then you select the full sheet. If you click on the triangle on the left, you calculate the full, select the full sheet, and then you delete it, and you paste your values again. So if I first copy them for myself, so I first delete them, so you make this empty. Okay, you make this empty, and then you select it again, and you paste your own values there. Or here, no, wait, go back. Let me just do it from scratch. Energy plus. So if I go to Europe, I go to Belgium, I go to Brussels, for example, I go to EPV. It's downloaded, then I go to my downloads. I change the extension. CSV. Yes, you say it might be unusable, but you say yes, and you see that now the symbol changes to the Excel file. If I open it, you get this column, what I showed you before. Okay, I select the first column. I click on data, text to columns, delimited. Yes, it's delimited with commas. I say next. It's not a tab, but it's a comma. So I unclick my tab and I indicate the comma. Next. And then you come to this, you say advanced, you click on advanced, and you change this to a dot. And then this you can change to a comma. Okay. Finish. And you will see that now my data is spread over the columns. I click on the triangle left up, I copy everything, Control copy, Control C. I select the first cell and Control V, and all the data are there again. So this is what you need to do for your own location. And once this is done, you will see that the graphs are generated. So if I go zoom out, why can't I zoom out here? View. There was something wrong, I'm not sure what. If you zoom out, here you see what the full content is of that sheet. So there are 4 graphs, and there is also a period that you can select with sliding bars. So if I zoom in again, so the first is the temperature hour by hour, and then the averages are automatically calculated. The 3 values, so the green one in the middle, these are these lines, these values you could even compare with the ones you had before to check if there's a big difference, yes or no. And here you see that I'm now for the, I think this is only for the, let me check. So I'm now showing 365 days, but imagine I only want to show the first month, so I have 31 days, for example. Then the graphs will update normally. Need to check if I need to do anything. So 31. Let me go up again. Then you have a smaller set of data. Normally you will not look at that because typically you will look at the full year, but you could maybe focus on something if you want, and you can also change it. So you can have 30 days, 31 days, starting from not the 1st of January, but the 1st of February, and then 28 days. So you could represent a single month if you want. But so let me put it back to 365. It seems I need to click on this again. I think it just takes time. So he will update, but it takes time, I think. Or I need to refresh somewhere. Data or calculation. Data. Enter. No. Yeah. It seems that the numbers are not working well. I think it's the layout. I think it's I need to click here while the bar is there. I think it has to do with the resolution of my computer actually, but okay. So if I yeah, you see I click on top, but actually it's the arrow that lifts up, so I think it has something to do with the resolution of my computer. But check if it wouldn't work, let me know, then I need to revise it. All right. So these are the first 4. Then you can also look at the wind calculation, but as said, so there is a wind calculation, and then you have the wind data results. If you don't do anything, these data, even though you pasted the data, will still be the one of the originals of Brussels. So what you first need to do is you go to the wind calculation tab below, and you have to click on calculate wind parameters first. Otherwise, it's not refreshed. And then you need to wait because it's calculating a bit. So you see my, it's still working. So, and then when it's finished, the finished bar will be there again highlighted, and then you go to wind yearly, and then the data are there. Typically, you have the files or the graphs as I've shown, so the yearly wind speeds, so the direction and the speed, the distribution of frequency, the distribution on a yearly basis of the speed over the day, and then a differentiation per month to see if there's a big difference in speed or either when it occurs during the day. You also have the wind roses on a monthly basis, so where you can both see the differentiation for speed and potentially also for direction if there might be a change over the year. Okay. Then I go back to my presentation to explain, but I see it's 11:30, so maybe we should have a break before I continue with the thermal comfort analysis. So let's have a break of about 10 minutes and then we start again. Did you all find cases actually? That's maybe important because next week we have the presentations. Did you all find a case? You're still doubting? Yeah. So what did you find? Yeah. 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 That happens. So what I would just keep what you have then. What you could do is look at another location and then mention it, but it's not so common that you have all the data. So just report what you have and indicate that the others were not available. That's okay. You delete it. You delete it. So don't leave the values of Brussels in because then you're combining two different contexts. So delete all the rest and just keep what you have. The estimated ones you can keep. So the estimated based on your latitude, so the radiation, the temperature, the sunshine hours that you can keep in there because that's correct for your context. But all the minimum or the extremes, you just delete them what you don't have because it's not correct. Yeah. Okay. Yeah, it could be. Just mention it in the paper then that you found these data, but it's unclear what it represents. Yeah, yeah. It happens often. It's that's why it's good that we have the hourly data because it will give you some additional input at least. Yeah, but you have the relative humidity mean and the temperature mean per month, so you can make a brief for the comfort analysis. You will only see then where it's located. Compared to the comfort chart, but you will not see day-night differences. Yeah. Any other questions on the climate data or the case studies? Yeah. 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 Okay. No. But if you know more or less if it's very old or new, that you can guess probably, you can, but you explain it. So if you explain that you don't have access to the very specific project with all the information of the architect and so on, that you therefore just selected something that is new or common or whatever, or that you had enough sufficient data, and then just explain what you have and what you think is important to have, but that you don't have, that's also okay. Yeah. Yeah. All right, let's see how we can then proceed with the comfort analysis on the same data. So it's actually quite easy because you don't need to put any new data, it's the same one. But what you now will see is that the graphs which we analyzed based on the monthly data last week will now be based on this hourly data. So it's this part in the spreadsheet, and you will see it on the tabs, but I will open the Excel file, that you have two different kinds of results, graphical results. First, for each month, you will see a line, but each line previously consisted of three values, the minimum, the maximum, and the mean, while now it has more values. Namely, it has for every hour, it has a value. So, for example, for each you have 24 values, and each value is an average of all the days in that month. So for January, for example, for this temperature here in the afternoon, it's 2 o'clock, but it's the average of the 31 values available for 2 o'clock. So it gives you, normally it will differ from your monthly values because this is a more precise way of calculating the average. And then what we can see, this is only one line, which is already is more precise than the monthly value, but it loses the information on how each day differs, because now we have an average day in January based on hourly data, but it could be that some days in January it's very cold and others it's very hot, or all days are more or less the same. So what the spreadsheet also allows you to do is for a specific month, not only look at this one line representing an average month, but looking at the hourly values to see how these daily changes occur. So for some contexts, it will be a very narrow cloud along this line, and for others, it will be a very broad or extended cloud. So the higher the variation is, the more spread the cloud is. The lower the variation is, so if each day is more or less similar, it will be a narrow cloud. So this is a better representation of what you had before, representing an average day of each month. So you have 12 lines, and on each line you have 24 dots, because each dot is 1 hour in a day, but that is calculated through the average of all the hourly values we have. So we could do it, for example, here for July or for August, summer month, and for January and winter month. And then we can see that it's always too cold, but that some days it's hotter than other days, of course. And the same for the summer. On average, it seems too cold, but actually most of the days in summer are, you feel comfortable with summer clothing when you're in the shade. So that's still important. This green zone is when you are in the shade, in summer clothes, sitting. So in Belgium, most of the time in summer you feel comfortable then, but there are days, even in August, that in the afternoon you will feel uncomfortable because it's just too not warm enough. While in winter you will never feel comfortable. So it's clear that we always need heating in winter time, Cooling is not necessarily needed. We will also not use heating in summertime normally, but it would mean that you need thicker clothes, or that you need to sit in the sun, or that you need to go inside and have a bit hotter. So that's how you interpret these graphs. And so it's up to you to, so first of all, we will gonna look at all, so this kind of graphs for everybody, but then you need to select 2 months and look at these in more detail. And which months you choose depends on the context. So sometimes it's a summer and winter month, but sometimes it's a wet and a dry season. Sometimes there's no differentiation, and then you only look at 1 month, so that depends a bit on the situation. So if I go back to my Excel file, here, yeah, then you go to the Olgier. First, you see these graphs for all months, which is representing the 12 months in a year. You see the green line again with the comfort zone, showing that when you sit outside in the shade with summer clothing, you don't feel comfortable. And then the graph below, it's zooming in just your monthly values. So it zooms in to see better what the data are. And then 2 months are here automatically shown. It's typically August, I think, and January. So August is below and January is on top. But you can also choose yourself which months you're looking at by changing the sliding bars here below the graph. So then you can say, I want to look at 31 days, and you choose the month. So for example, I want to look at January, then I go back to the beginning, and I keep my 31 days, and then I see the January month. So that allows you to focus on the months that are more interesting for your specific situation. If it is July and August, you can keep these graphs. If you want another zoom in, you can use this tab to do that. All right. Now, these are the different steps in the first part of the paper. So the first part of the paper, you will first describe your context, your case study, and then you will describe your climatic analysis, monthly data first with the comfort analysis, and then the hourly data with the comfort analysis again, and then we go to the solar analysis. As said before in the first lessons, it's important to check if you can learn anything from old architecture or vernacular architecture in your context to understand how new buildings are doing wrong things or do take into account these lessons. So typically, and that's why I'm going to present a case study in Cuba to show how architecture has been influenced by the climate there, but also it's typically architecture is not only a result of climate. Often it's also about culture or about how dense people need to build in a location and so on. So it's not that easy to always pinpoint what's coming from climate and not. So the intention is more that you try to find some literature or text on your climate or where you're building in and try and the vernacular architecture and try to grasp the main points. So if we look at Cuba, what we see here, temperature-wise, it's a hot climate. So it's always above 20 degrees. The variation is not too big. So throughout the year, it's a quite stable climate. So it's not that we have a real cold winter and a warm summer. It's more or less comfortable throughout the year, but it can be quite hot, especially during July, August. We see the highest extremes, but also in winter. There are also days where it's too cold. So although we would not expect the need for heating, and they don't have heating there, we see that it can be uncomfortable in a few days a year, but these are rare, so it doesn't happen too often. So it's a warm climate. The question is now it's humid or dry, therefore we look at relative humidity, and then we can see their high humidity. So it means it's a warm, humid climate. So typically, if we look back at the vernacular architecture we've seen before, in this context, we need ventilation to feel comfortable. So we need solar shading and ventilation to ensure that our heating or cooling demands, are as low as possible. So always humid the whole year round. So it's always, so it means it's difficult to sweat when it's too warm. So that's why this ventilation is important to feel comfortable. This is the radiation where we see that on the whole year around, with some exceptions, that the diffuse and the direct are more or less the same, meaning that you have moments or days or hours per day where you have a clear sky, and you have hours or days a year where you can't see it here if it's on a daily base or hourly base, that it's very cloudy. So what we could imagine is that you have hours, for example, in the morning where it's blue sky, and that clouds are forming by noontime, and then you have a rainy afternoon, for example. So this, I could imagine that it's happening like that, because we see that it's humid. Oh, sorry, to go back. It's humid, it's warm, and we see from the radiation that there is both diffuse and direct radiation as well. So there must be also rainy periods with afterwards a clear sky again. What does it mean if we look at the thermal comfort? So we see that it's on the right top of the comfort zone, so hot, humid. If it would be dry, then it would be more to the left, but it's hot, humid, and that's a difficult situation for feeling comfortable. As we said before, when this is this angle that is cut off from the comfort zone, because it's really difficult to feel comfortable when it's a combination of warm, high temperatures and high humidity. This is an August month where we see that the cloud is quite narrow, so it's every day is more or less the same, and there's quite a big difference between morning and evening. So the highest temperatures in the afternoon, we see that the humidity is lower, while by the afternoon or evening we have lower temperatures, but so the relative humidity becomes higher. While in January, we see, although the line is very close to each other, we see that the variation is much higher. So it means that in January we'll have a mix of warm days and colder days. So some of the days are completely under the comfort zone, meaning that actually heating or thick jumpers are necessary to feel comfortable. So, as a conclusion from the analysis, we can see it's a tropical, or it's a very warm and humid climate, which means that to make it comfortable or to reduce the cooling demands, we will need ventilation and protect ourselves against the sun. This is Havana with the very dense, so capital city in Cuba, where we see this rigid grid, which has to do with nothing to do with climate, but it's urban planning to do. But what we can see already here is that we have a context where we need ventilation in a very dense city. So the question is, how can we achieve this? And here you see a picture of the architecture. What we typically see in Cuba, for example, or in Havana at least, where we have higher buildings, is that the ground floor is typically open with a deeper ground floor, and then the upper floors. So you have kind of a corridor which actually serves as a protection against the sun for people walking in the streets. So here people walk typically underneath. Why? For protection, but also for the rain. So it typically rains a lot, like it's humid, so people are protected when they walk there. And another thing that you can immediately see is the courtyards, and that's necessary for this ventilation, because if you would have a fully closed building, it would be really hard to have this ventilation working well. So this is the courtyard you see here. So it means, again, we need this to cross-ventilate each room. And you see typically also that people work with internal balconies and overhangs for protection against sun, but also rain. Another example of such internal courtyards. Now, these internal courtyards have not been there long back in history. It's actually quite recent if we look at the long-term history. Why? Because originally Havana was not that dense. It were so the number of buildings were lower and typically not that high up. So typically you had just one floor originally, and then as more people start living there, one had to densify first on the ground floor and then also in the height. So originally, typically, more the rural architecture was there, and which is still seen. So if you have a plot, the green area is the open area, and the white parts are the built-up areas. And here you see the three-dimensional view. So you had a lot of open space, and the built area on a plot was quite limited, which made it easier to have this ventilation and assure comfortable climates. But as it became denser and denser, people had to build next to each other. So instead of open spaces between the buildings, we saw more and more the terraced, so the really row typology appearing. And then even on the plot, when families joined, for example, two families on a plot, we saw that the backyard became filled in more and more. So originally, it's the full front facade facing the street that was fully built. But once that was filled, people started also building on their plot themselves, more to the back. And originally it was still ground floor, so here with the open space for ventilation, but also to have a common space with a family to share a private open space, let's say. And then more and more, when the population increased, we see that once the plot was completely built on the ground floor, one started building one level on top of the other, but still keeping this courtyard open. So instead of, so if there are higher needs, one could also have just built the full plot, but one didn't do that because of this climatic context, but also to have a common space outdoors shared by the people, the different families living on one plot. And that's how, step by step, these courtyards started to appear in the architecture, but always combining or trying to have a good ventilation, protection against the sun, but still sufficient daylight. That's becoming sometimes difficult. The denser one builds, of course, and the higher one builds, the more difficult it is to get daylight at the ground floor. Now, by doing this and by getting more and more higher, these courtyards become more critical if they still function well, yes or no. So what happened then is that different designs became apparent for really focusing on the courtyard and making very detailed simulation on how the wind flows. More and more the front needs to be an important task is to keep the sun out. So there we see balconies appearing to have an outer space, but then with the shutters, the wooden shutters or the louvers appearing in the street. And then typically more and more in densities, the front is becoming public space again. So there you have the open corridors appearing, and then only one lives in the upper floors. And then the ground floor becomes only partially used for residential purposes. So that's how you here see it appearing. The more this becomes closed, the more difficult it is to get the ventilation right. And then sometimes shafts or ducts, vertical ducts, are integrated with openings, just to have this wind current appearing. So if we would only work with the courtyards, it would be, the wind speed would drop dramatically, and people need more and more active cooling. So that's why just vertical elements, so the hot air rises. What one does is have openings through the, so every house is connected to these shafts, and then the wind can blow in there and actually because the hot air is raising, it actually extracts the air from the houses to this shaft, and then it goes out. So here you see such a picture of, so it has no quality anymore. It's small, one cannot enter it. It really has just a function of ventilation. While here, the courtyards originally had a double function. It's a space where one can go from one building or one house to the other. It's a meeting space. There can be trees inside, so it's a very different quality there, of course. And as one is more and more closing everything, the dimensions of these courtyards will become important. So even if you just have an open space, if it's too narrow or it's too not high enough or whatever, it seems that it has a big influence on how the wind can enter. And that can only be calculated or simulated with simulations. So if we look at, so if we take a section through this building or through the plan, we can check, so if the wind blows in from this side, so that's the wind direction, so it would go there through the first house into the courtyard, should go through the second and then another courtyard and through the third. So the question is, does it really reach this whole line? And that one can really simulate, so to check what happens. So there are models where you put your building in, like energy simulations, but not looking at thermal comfort due to or heat or temperature, but how the wind is blocked somewhere or bounces against some surfaces, what happens with the wind speed. And so you see here the wind, the darker the color, the higher the wind speed. That the wind speed here, so it goes on top of the building and it enters here. So you see that here it will be much more difficult to have good thermal comfort, because it's less ventilated, or here again, it's less ventilated than when you look at these upper spaces. So it really depends on the location even of the rooms, and then it can be checked how the design can be improved to get the wind deeper, for example, by changing the dimensions or the height of rooms and so on. That's something we won't do. I just want to mention that it's there now, really a topic of the design of housing. The courtyard design is part of the design now, to ensure that with these higher densities and these higher buildings, it's still the wind can still sufficiently enter the different rooms. Another program that I just want to show you that we will not use or not mandatory use in the course, but you can use it if you want to make some next steps or have some nice graphs, because that's what this software does. So what I gave you is some Excel files with some very basic outcomes. So the graphical representations are not very they're just graphs, but there is software which allows you to make very nice outcomes, just better or nicer presenting the outcomes. It's more or less the same outcomes, but nicely presented, which can be helpful, for example, if you need to participate in a design contest and you want to show that you are aware of it and you want to have nice graphs, then this software is a nice one to use. It's called Climate Consultants. It's a free software. And it's actually doing more or less the same thing as we do. So it's using the same kind of weather data. So the hourly data, the test reference year data that we are using. So it's from Energy Plus. You see it mentioned here. So the same file that you have now downloaded for our Excel file input, you can also input it in this software package. And this is then the tables that just represent, for example, the monthly means that they calculate, as we did as well, but here it's a table. And then you can, for example, have this kind of nice graphs showing mean value. So it's a bit nicer presented than we do, but actually it's the same kind of information. You have it here for it's the temperature, I think, yeah. So it's the temperature for a certain location. For every month, you see the average, the mean, minimum, and maximum, and then the extremes, as we did with lines. Here it's with bars, and then you see it also on an annual level. This is in Fahrenheit, but you can also change to degrees Celsius if you want. You can also have graphs on temperature and humidity showing on one graph per month, for example. So I did it here for Belgium just to show you. For Belgium, again, you can show also the radiation for each month. Again, direct, diffuse, or the global. And then you can also do a thermal comfort analysis. Here not using, so it's the ASHRAE chart which is included. But which is nice sometimes to learn from is what you can do. So what they also mention always to achieve comfort, what the strategies are that you can put forward to improve the thermal comfort. So that could be something interesting to see, but it's typically, it's quite evident what they say. So it's something that you should be able to do by yourself. So it's like shading, foresee shading, or increase ventilation, or dehumidify in the most extreme cases. But these are the learnings that you should be able, or the recommendations that you should be able to formulate yourself, actually. You can also have these graphs on solar radiation, but so really making solar charts. But we will learn that in the next module. So we have not touched on the solar charts until today, although these are integrated in the software. I would not look at these yet, because we will have the next modules on solar axis and solar charts to have first the theory behind and how you use them and how you represent things before having a look at it here in the software. And then I come to the second assignment, which I think is quite clear already from what I told you today. So we will now go to the analysis on based on hourly values, meaning that you need to find the data for the same location, and you put it in the Excel file in the module as I've shown, and then you integrate the graphs, the outcome in your paper later on. So what you need to do is download the hourly data, change it to the correct format. Once you have the data in the correct format, you copy paste it in the Excel file, and you save the file again under the certain name, as I said before. So the latitude, then test reference year as the file name actually, and then your country, your country, your city, and then your own name. Then you will look at all the graphs and integrate these in the paper, both on the climate analysis and the thermal comfort analysis. So it's the same Excel, so it's all the same input, just another output chart that you need to look at. So look at all months, and then look at some extremes, either a summer month and a winter month, or a cold or a dry month and a wet month. It's a bit up to you. If there are no two extremes, you just justify that you're only looking at one extreme because there's only one. And then it's important, of course, to interpret what you get out of it. So you learn from your analysis in which kind of climatic context you're working, and try to link that to the vernacular architecture that you know in your specific context, to see how it fits as measures to make it as comfortable as possible, and then make recommendations for climate conscious design in your specific context. That's the aim. Now, next week, it's a lesson with presentations. So it means that besides the two assignments you got until now, you also need to present a PowerPoint. And as I would like to let people, as many people as possible, present in one session, it's a quite strict guidelines on what you can present and how much time you can get. So that's why I really want to have it in the same format for all of you, so that you can also quickly follow the other presentation, because it goes quite quickly, and if everybody has a different structure, it's really difficult to get into it. So that's why we have quite strict requirements on how you present it. So it's more or less 10 to 11 slides per person, meaning that you present 6 to 7 minutes, more or less. That's how we will organize it. So it's 1 to 2 slides with your case study, which is the location, of course, an image and a plan, a section maybe, and how it's and the context where it's located. Then 1 slide with the climate data based on the monthly values. So this long table, you just put it on 1 slide. Then the thermal comfort based on monthly data. Then we step to the hourly data. So the second assignment. So first you represent the temperature, the relative humidity, and the solar radiation, and then the comfort. First all months, and then the 2 or 1 extreme depending on your context, and 1 slide with the wind analysis, and then your final slide with what you learn now from it for a good climate conscious design in your specific situation. The presentation, it's again the same, your latitude, it's called presentation 1, your country, city, and your name. And how do you submit all the assignments? So there are in the discussion board on Toledo, there are 3 discussion boards already created. So the first assignment you submit there in the first discussion board, the second in the second, and the third in the third. And you all submit all of this by Tuesday, 1 o'clock, because then I will work on it to make one presentation out of it. So that's why I need it beforehand. So I'm not sure if you know the discussion board, but if you go to Toledo, here you have the discussion board on the left-hand side. And if you go to that, you will see that there are 3 assignments. So the first 2 assignments and the presentation. So why do we do it like that? Because then you can also always have a look at the others' work done later on if you would like to. The only issue I have for next week, that I need to be in the city center of Leuven for a meta-forum discussion with other professors at 12 o'clock. So I only have until 20 to 12, or either we start a bit earlier, but I'm not sure if you have other courses before you have. So then we will start at, as foreseen, 10:30. I will maybe check with Professor de Trooijer if he could take over the second hour then, so that we can have as many presentations as possible. So I will select who will present, so everybody submits. If you don't get the chance to present now, don't worry, you will get a chance on the next session. So we will distribute it a bit. And